Okay, welcome back to part 2. We went through some different problem cases and conditions and special cases of linear acceleration or rigid body acceleration of fluids. So this second half, we're just going to look at rotational or centripetal acceleration of fluids. And again, this is rigid body. So if we think of none of the fluid particles are moving relative to one another. They're all moving with the same, motion. They're moving together. So recall our general form of our equation. We said that the gradient of our pressure in a fluid that's undergoing rigid body acceleration is equal to the density of the fluid times the vector sum g minus a. So this is very useful in linear coordinates, or Cartesian coordinates for linear acceleration, but it's more useful if we can write this in a polar coordinate system or cylindrical coordinates, and when we're talking about a rotating fluid. So for cylindrical coordinates, we would have, if this is our let's draw a bit of a top view of our cup. Let's imagine it as a cylinder. So going straight up the center of our cylinder is our z-axis. And we would have, if we had Cartesian system, our x and y, maybe something like this. But in cylindrical coordinates, we have our position vector along our r coordinate direction. And we have a theta coordinate direction, which is our transverse coordinate. And then finally, we have our z coordinate. So this position up at the top, our radial coordinate is always going directly from our z-axis. Our theta would be measured from some reference axis. So here I'm just drawing it as our reference axis would be that same as the x-axis. And then this position here would be our z coordinate. So this point right here, if we were at a point right here, would be r, theta, and z. So if we rewrite our pressure gradient in cylindrical coordinates, and we assume cylindrical symmetry, so that means we have a container that is symmetric in the theta direction. So we can rewrite this in cylindrical coordinates. If we assume cylindrical symmetry, so that means the partial derivative with respect to theta is just going to be equal to 0, regardless of what we take the partial derivative of. So our new equation becomes our gradient of pressure is equal to di P di R in the radial direction plus di P di Z in the K direction. So what on earth does this mean? Well, let's look first at what's happening inside of a rotating, or a fluid that's in a container, and the container is undergoing rigid body rotation. So in this case, we'll define a few things. The axis of rotation is going to always be where our z-axis is for our cylindrical coordinates, and we'll define our angular velocity as omega, and omega here is just drawn as a rotation, but omega would be a vector, and that would be acting in the positive k direction, in this case drawn here. So this would be omega times k hat. And our position vector r is equal to r times I hat, or ri hat. So at any point on our fluid, so if we look over here now, we'll have an acceleration term, which is going to equal to negative r times omega squared. If we think back to our definitions in dynamics, this would be the radial component of our acceleration, or our centripetal acceleration. And then the other component of acceleration that we would have is our gravity. And now, because our centripetal acceleration is a function of r, it's going to change depending on how far away we are from that rotational axis. So if that's going to change, that means our acceleration is going to change. And if our acceleration is going to change, that means our surface is going to change as well. The slope of our surface is not going to be constant, it's going to be curved. And it just so happens that for liquids undergoing rigid body rotation in a container, the shape of those isobars in the free surface is a parabola, or in 3 dimensions, a paraboloid. So let's write some equations down. So we said that angular velocity omega is just equal to some magnitude omega times k hat. And we said our radial position r is just equal to some magnitude r times I hat r, or IR hat, which is just the unit vector in the radial direction. And then our centripetal acceleration is just going to be pointing inwards in the radial direction, and from rigid body dynamics, it would be equal to our angular velocity cross product with our angular velocity cross product with our radial coordinate. And if we simplify this, this is just equal to our distance from our z-axis, our radial distance, times our angular velocity squared, and that is acting in the negative IR direction. So notice that there's a negative term here. So A is always acting toward the center. So if we write our equation for our pressure gradient now, grad P was equal to rho times G minus A. This would be equal to rho times minus G in the K direction would be our gravity, and then our other acceleration would be minus minus r omega squared, so plus r omega squared IR. So this would be our definition of our pressure gradient in vector form for our rotating fluid. So remember, if we go back up, we wrote somewhere this form of the equation. When we wanted to write this in terms of our cylindrical coordinates, we knew we would have some term that was pre-multiplying the radial coordinate and some term that was pre-multiplying the vertical k direction or z-axis coordinate. So if we compare those two equations, when we go back down now, we recognize that we have this term and this term. So if we equate those two, let's say, remember, we said the gradient of the pressure was equal to dP dr I hat r plus dP dz k hat. So both of these equations are correct and they're true. If you believe they are, we can also write dP dr must be equal to rho times r times omega squared. And dP dz must be equal to negative rho times g, which is equal to negative gamma. So we have equations now for each of our partial derivatives of our pressure. Partial derivative of pressure with respect to r, and partial derivative of pressure with respect to z. So how can we find now one equation for our pressure as a function of r and z? So there's 3 steps to do this. The first step is we're going to take our derivative dP dr, and we're going to integrate that with respect to r. And we're going to hold the z coordinate constant. So we're integrating p with respect to r partially, and by partially I mean we're just going to hold z constant. So we have dP dr is equal to rho r omega squared. So we can say our pressure P is equal to the integral of partial derivative dP dr dr. So we're integrating just partially with respect to r. And from our equation above, if we integrate that, we end up with 1/2 rho r squared omega squared. And because we're integrating this indefinitely, we have to add some constant of integration, and that will be some function of z. Because we didn't consider z, we held it constant, there's going to be some constant function now through z. And this will be our integration constant. So once we have this equation, we're going to differentiate this equation now with respect to z. And if we do that, we could look ahead. All we're going to have left is the function of z, or integration constant, prime, or the derivative of that. So now dP dz the derivative of this function up here, up above, with respect to z, this first term is a constant, so that would just be 0, and all we're left with is f prime of z, the derivative of that function fz. And then we also know from before, we have an equation dp dz is equal to negative gamma. So this must also be equal to negative gamma. And we have an equation for d rho dz. Now let's integrate that again with respect to z, and then we'll compare our two integrated equations, and we'll try to solve for our integration constant, that unknown function. So we can write the integral of f prime z dz is just equal to the function z. And if the function z prime is equal to gamma, we integrate negative gamma, and we get, so negative gamma dz, which is equal to negative gamma z plus some constant c. So finally, our equation PR, pressure is a function of r and z. If we combine these two equations up here, 1 and 2, or I guess subbing 2 into 1, then we get our function p is a function of r and z is equal to some constant c minus gamma times z plus 1/2 rho r squared omega squared. And if we want to find this integration constant, so if we assume that p is equal to p0, some constant point or some pressure that we know, at z equals 0, r equals 0, then we can just write p0 is equal to p at 0, 0. And if that's the case, we can solve for our integration constant. That integration constant is just equal to that p0. So that's just equal to c. So then we can finally write our equation. I see I flipped the z. Let me just fix that. So our function, our pressure function as a function of r and z is then just equal to p0 minus gamma times our z position plus 1/2 rho r squared omega squared. So that is the function for our pressure in a liquid that's undergoing constant rotational acceleration or constant rotational velocity or under centripetal acceleration. And if we rearrange this, we can get an equation for z rearrange for z, and we get z is equal to p0 minus p1, some other pressure, plus r squared omega squared over 2g. And if we recognize this as a form where we have a constant, and then this section right here could be another constant, then we basically have an equation a plus b r squared. And this is the shape of a parabola. So it's just a parabolic expression. So we know that the variation in z is linear and the variation r is parabolic. And the parabola is always concave up. And we know this because we look at this term omega squared, the angular velocity. It's going to be positive and 2g. So that shape is always going to be upwards. So if we combine this thought, these last 2 points, we can say all isobars are parabolic. So if we go back to that picture, then we said this isobar P RZ is equal to some constant pressure, PA, is going to be parabolic. And the isobars are here. And one other interesting line, which is just a straight line when we're talking about linear acceleration, but in centripetal acceleration, we have our gradient line, and it is not a straight line anymore. It changes as you change your depth in the fluid. So this would be our gradient line. So our gradient lines, just capital GL for short, are always perpendicular to the constant pressure surfaces, or to the isobars. So if this is true, then the slope of our gradient line, which is just dz dr, so just evaluated along a constant gradient line, is the negative reciprocal of the slope of our isobars. So that's -1 over the slope of our isobars, dz dr of our isobar. So we know dz dr if we take the derivative of our function up above for a constant pressure line right here, highlight this in the red, take the derivative with respect to r, the first term goes away because it's just a constant, and we're just left with r times omega squared over g. So dz dr negative g over r omega squared is the negative reciprocal of that. So then if we integrate this, we can get a function for our gradient lines. Some integration constant C1 times the exponential negative omega squared Z over G. So this is our gradient line. And if we go back above, this was our isobar. And notice that our gradient lines, we don't have any gamma term in here or a rho term, so it doesn't matter anymore what our density of our fluid is. All right. So how would the height be affected if it was a closed container? Now I'm not really sure off the top of my head how that would work, but I think we could apply the same analysis that we would previously, where you imagine the fluid increasing to determine your fluid height. Maybe I can explain it a bit better when we have our example. So let's just keep going and we'll come back to that question. So what I mean by these gradient line equations, the position R of our gradient line as a function of Z is some constant C1 times the exponential negative omega squared Z over G. So in the absence of friction and Coriolis effects, which is another acceleration effect, this equation defines the lines along which the apparent net gravitational field would act on a particle. So it's kind of a difficult concept to grasp what is a mean gradient line. So if we just imagine this is a snapshot of a rectangular container and it has these stringers, and these stringers want to float, and they're going to float as things do in the direction, they will line up in the direction of that pressure gradient or decreasing pressure. So they're going to line up along the gradient lines. So if we have a fluid that's static, fluid, and a fluid that's rotating, then we can see that these stringers are always going to follow that gradient line. So depending on the density, a small particle or bubble would tend to rise and fall in the fluid along these exponential lines. So that's just the gradient lines kind of visualized. So the next thing that we need to find if we're going to define pressure changes in a fluid, it's really useful, is to determine the equation of the free surface. So after we have some fluid, it's in a symmetric container, it starts to rotate. We have some equations for the isobars. We need to figure out what is the actual height of the fluid now. And we can do that the same way as we've done with a linear accelerating fluid, is by finding an equivalent volume. We're not having any changing volume. So we can apply this analysis the same sort of manner. And it's important to note here that this applies to this analysis anyway, applies to cylindrical containers only. So if we have a cylindrical container, then we can find our equation of our free surface. So if we said our pressure was equal to P0 and Z was equal to H, this would be our free surface. Then the function H, which would just be Z as a function of R that we had, would be 1/2 rho R squared omega squared over gamma, which we could just write as rho R squared omega squared over rho G. And we can get rid of these rho terms. And then finally, we're left with omega squared over 2G times R squared. So the equation of this surface H as a function of R is equal to omega squared over 2G R squared. So that is the equation of our free surface. So now we need to figure out, okay, what is this value of H over here? What are these quantities? And then lastly, what is this quantity here? What is the height of the lowest part of our fluid? So let's do this by considering or equating the volume of the total fluid. So the volume of the fluid that must exist is the volume of the fluid before, which let's call capital H. Draw a different color. So H would be resting fluid height. I swear my iPad gets tired too. Resting fluid height. Z is the height of the lowest point. So that's when R is equal to 0. And then lowercase h would be equal to the difference between the highest point and the lowest point. Or we can just call h at R minus h at 0. So for a fluid in the container, we'll conserve the volume. So the total volume before, when it's at rest, has to equal the volume when we have acceleration. So the total volume before is going to be equal to pi times r squared h. So that's the volume at rest. And this must be equal to the volume afterwards. So the volume afterwards, if we consider the volume of this whole region here, and if we subtract the volume inside the parabola contained within that free surface, we can get the volume of the liquid after. So the volume of that whole section would just be pi r squared times z plus h. and subtract the volume inside the parabola. The volume inside the parabola is given up here is equal to pi over 2 r squared h. So if we rearrange this, we can solve for z, and z is equal to h, which is the initial height of the fluid, minus our angular velocity squared times the radius of our cylinder squared divided by 4 times g. And quite interestingly, h is also equal to z plus h over 2. So if we redraw this over here, let's continue this line. If h goes right to this line here, oops. These two quantities at the side become h over 2, h over 2. And then our equation for h becomes omega squared r squared over 2g. So the initial height of our fluid before it experiences acceleration is the midpoint of the difference in the height, h, after we've started rotating the fluid. So this is midpoint. That line. And it's actually equal to h. So let's try to take that in and chew it up with an example. So this is a example where we have a coffee cup, and it's asking what is the angular velocity that will cause the coffee to reach the lip of the cup? Basically, how fast do we have to spin this cup before, right at the instant that that liquid would start to spill out the sides? It says it's initially filled up to 7 centimeters. And at this point, what is the gauge pressure at A? So right when it starts to spill, what's the gauge pressure at A? So where can we begin? Let's write down some equations that we know. If it's initially filled to 7 centimeters, that would be our capital H value. And from that, we can figure out what our new h, or our small h value is. So if h, capital H is equal to 7 centimeters, what is our small h? So we know h, capital H, the initial height of the fluid, that's going to be the right in between the highest and lowest points once we have accelerating. So if we know this is 7 centimeters tall and we have 3 centimeters here, that means this whole distance (3 centimeters below and above) will be h, right? So this whole distance is h. So if this were drawn properly, the surface would actually come all the way down to here. Something like this. So don't let the scale of the question throw you off. So if this is the case, then h is actually equal to 6 centimeters. And we know from our equation above, if we wanted that h value to be 6 centimeters, we'd have to follow the equation for h, omega squared r squared over 2g. This is equal to omega squared r squared over 2g. So we could rearrange and we would get omega is equal to the square root of 2 times g times h over r. So r is equal to 3 centimeters, sorry. G is equal to 9.81 meters per second squared. And h is equal to 6 centimeters. So if we substitute those in, we would get omega. In order to just get the coffee to spill out of the mug would be 36.2 radians per second. So that question, the initial diagram kind of throws it off, and I put an extra note here that this is not to scale because it doesn't show properly what that distance 7 should be. It probably should have drawn 7 exactly in the midpoint between the top and the bottom of that parabolic shape. So the next question is, what is the pressure at point A? Let's assume that A is actually right at the bottom in the corner. So it's when r, lowercase r is equal to capital R, and at the very bottom of our container. So Z is equal to 0. So pressure at the bottom. Our equation for P was negative gamma times Z plus 1 half rho r squared omega squared. So at the very bottom, our equation for Z would be the total height of the fluid above. So that would be negative 0.07 minus 0.03. And then our radius is right at the edge, so radius is 0.03 meters. Our pressure at A becomes 990 pascals. So our z-axis is from the center of that fluid. So as we rotate that fluid, that z-axis is going to move up and down. So the distance we're looking for is the distance from here to here. Let's look at another case. So in this example, we have a tube assembly. It's completely filled with water such that the pressures at C and D are 0. So notice that it is sealed. If the assembly is given an angular velocity of 15 radians per second, determine the pressure difference between A and B. So these are sealed. And the initial pressure at those points C and D are 0. For the last question, pressure at A. Yeah, so if we go back up to the last question, we had our equation or our pressure right here. And this was reference to R and Z. So R and Z is going to be sitting right there. Where are we? Okay, down here. So this will answer your question. If you had a sealed container, how do we solve this problem? So let's use our equation for that pressure again, except now we're going to solve for the pressure at 2 points, so the pressure difference. So it's asking for the pressure difference between PA and PB. So we'll do PB minus PA will be equal to negative gamma times ZB minus ZA plus 1/2 intensity of water times omega squared times RB squared minus RA squared. So that's our pressure equation. Now all we need to do is figure out what on earth is ZB, ZA, RB, and RA. Start with Z or Z. What is, or maybe it'd be easier, what's ZB minus ZA? What is the difference in the height of the water column above point A and above point B? Let's start with ZA, might be straightforward. Yeah, 0. So ZA is 0.6. It's this distance here. The height of the water column, the fluid column above point B is also 0.6. So this quantity is just 0. And then what about RB? That's just equal to R, capital R. And RA is right at that Z-axis. It's where the rotation is happening, so that's 0. So then we can simplify that equation. And we can write PB minus PA is equal to, first term goes away, so all we have left is 1/2 rho omega squared R squared. So that's 1/2 times 1,000 kilograms per meters cubed times the radius, or omega squared, is 15 radians per second, times big R, 0.5, and both of those terms are squared. And we have left 28,125 pascals. So that's the pressure difference between point A and B. Are there any questions about? I feel like there might need to be some time sinking in for some of these questions, but these two examples cover a pretty big range. There will be a lot of problems in the problem set next week for rotational or accelerating fluids, but I would say this slide 30, has some key equations as long as you understand what they mean. And this slide here. So this is the top one here, pressure distribution. The equation below that is the equation for an isobar. And then if we go back down here, if we have an accelerating fluid in a cylinder, or rotational fluid rotating in a cylinder, then we know some things about the container. The initial height of the fluid is going to be the midpoint of that parabolic shape, so halfway up that parabola. So the distance z plus h over 2 is equal to h. So we notice right here, this term, this equation, this term right here is actually equal to h over 2 if we compare it to this term up in this corner. It's just divided by 4 instead of divided by 2. So that's probably the biggest thing to look at when we're solving problems, and that's what made this first problem easier once we recognize that we want to spin it fast enough that it goes over the top, and there's 3 centimeters above where it's initially at rest. I mean, a better diagram would have maybe made it a bit easier, but recognizing that h over 2 is 3 centimeters, or h is equal to 6 centimeters, then suddenly we can solve the problem because we have an expression relating h to that rotational velocity. So we'll leave it at that. And this is a quote from Napoleon. And it is, "Ability is nothing without opportunity." And yeah, I like this quote. I thought it was pretty important. Doesn't matter what you're able to do if you're not able to do it, if you're not given the opportunity to do it.